Hello everyone. Today I want to move into a new topic that we explored just briefly back a few lectures ago, and that is input-output ports, often just referred to as I/O ports. Okay, this is covered in chapter 4 of the course notes, and referring to a diagram that we keep coming back to, basically the high-level block diagram of our computer system. The aspect that we're going to focus on now are going to be input and output ports, and we'll look at some ports or how to design a port that can be both, well, not both, can be selectable between an input or an output. One of the things that I mentioned back in the last lecture when talking about memory maps is that computers tend to map their I/O one of two ways. So I/O that's mapped let's say mapped in same address space as memory is referred to as memory mapped I/O. Okay. But we can, as I stated, and we didn't explore too much, we can have I/O can have its own, let's call it I/O space. And in this type of configuration, a separate I/O map will exist. So we mentioned this before. One of the things that I didn't mention is when the I/O has its separate, its own I/O space, we have an additional control line. So an additional control line on the control bus that's typically something like IO/mem, something to that effect. Basically, in one state, and it could be the opposite, right? It could be IO/mem, where in this case, when line high I/O space is being accessed, and of course when low memory space. Okay, and then this one, of course, is just an opposite version of this. It'll depend on the architecture of the computer on what the logic is. Okay. So this is just the same idea, but with reverse logic. Oops. Okay, so let's look at what a simple I/O port might look like, and with its interface to our bus structure. Okay, so here's a simple I/O port. This one has a separate input path and a distinct output path. Again, we're going to look into different types of I/O ports where a port may be purely input, purely output, or often configurable between one or the other. So what you'll note right away that this looks very similar to our single bit memory device that we looked at previously. Okay, and if I pull that one up just briefly here, we'll see there's a lot of similarities between the two. They both have will make use of some kind of address decoding to locate it at a specific address in memory. We see that the I/O this I/O device is mapped at a different location than this memory device. These might exist in the same system, so we want to make sure that they have unique addresses. And we see a similar interface to the write and the read lines, okay, that are only enabled when this specific device is selected. Maybe let me use, okay, so we have a write line that only gets selected when we have the address decoder's output active, and we have a read line that will also only get selective when the address decoder's output is active. What's unique in this particular example is that the write signal is only going to an output port, because of course generally you're only going to be writing to an output, and the read signal is only associated with the input port. Okay, so again, a little bit of distinction there, where in the case of my 1-bit memory down below here, when we're reading, we're actually reading the data that's stored in that, in this case, the D latch, or we're writing to that D latch. Here, what an I/O device is, this is something that's allowing us to interface to the world outside the computer. Okay, let's get rid of this now. Okay, so it's allowing us to interface to the world outside the computer. So, you know, as an output, we may be using, you know, maybe this is our computer, and this is now a pin that's externally accessible on the computer. Okay, and so we might interface a display to that output port so that we can illuminate it as required, in this case a simple LED. So we can write a value of 0 to that output port to turn that LED on, or write a value of 1 to turn that LED off, and it will stay on until on or off, whatever state I've set in, until we change it, because that value is stored in this D latch. I don't need to hold the value on the data line. I can write that value in through this path to the latch, and it'll get stored there and the data bus can be freed up to do something else. Okay, in the same way, I can use this this input here to read the state of some kind of input, maybe maybe a push button switch, for example. So I could have a push button switch that I'm reading the state of every time I activate a read, right? Which happens when I put a read signal on the read bus and the appropriate address on this address line, in this case 10101, which will activate this chip select signal, which will now turn on this tri-state buffer to allow the state of my switch to be read in onto the data bus and read a value of 1 if the switch is not pressed, or a value of 0 if the switch is pressed. Okay, like we did with sorry, before I go on, I just want to again point out that it's clear in this example that there's no extra control bus signal or line here to select between whether we're talking to I/O or memory. So this is an example of an I/O device that's memory mapped. It's mapped in the same address space as is the memory that I had up here and had deleted. Okay, so this I/O device would show up as an element in the memory map for this particular computer. So as we've like we've done with our our memory devices, we can look at a timing diagram for reading and writing to our I/O devices as well. Here is a timing diagram for a read from the input port. Let's say read timing diagram. If you look back at the timing diagrams that we investigated for our memory devices, you will see that it looks identical. Okay, we put the address on the address bus. In this case, we have a different address because it's unique to this I/O port. Let's clean this diagram up here. Oops, actually I can leave this here. Okay, when that device is presented, or when that address is put on the address bus 10101, the output of this address will become high. That'll put a high on both inputs to the AND gates. But then when we also make the read signal go high, now this read signal, which is tied to the tri-state buffer, will be activated, and this tri-state buffer will be enabled, which ties the whatever is on this input, whether it's a 1 or a 0, will get read onto the data bus. And after some delay, some access time, the value that was on this input port will will appear on the data bus. Okay, and we will let that as long as that read signal remains high, the value will stay on the data bus, and then once the read signal is deactivated, that will cause the tri-state buffer's output to float, and of course our data bus will also float, and it will be free for some other device to use. And of course the address bus can also be used by some other device. It can change value and be used by some other device at this point. So this, again, compare this to the timing diagram of our memory device, and you'll see that it's identical in the steps that are required to read from this device. And in particular, this particular device does not have a separate I/O map. This computer, we can see that because there's only a read and a write signal on the control bus. There's no I/O mem signal. So this I/O device is mapped to the same address space, the same map as the memory, and that's why we call it memory mapped I/O, and it's therefore accessed in the exact same way as our memory. If we go and just duplicate this diagram here, and if we go and look at a timing diagram again for a write cycle. Okay, so let's bring in this timing diagram. So here, again, you should note right away that this timing diagram looks identical to the write cycle of a memory write cycle timing diagram. The only difference is where the data is going. Okay, here the data is going to and outputs some external connection to the computer. Okay, but again, process the same. We put the right address on the address line. 10101 causes the chip select line to go high, puts high on both of those. Okay, so that happens when we put that address on the address bus. We make sure that whatever data we want to be written into the device is already on the data bus, just like we do with a memory. And then we activate the write signal, in this case by bringing the write signal high. So when we put a value of 1 on the write signal, that causes this output to go high and enable the D latch. When the D latch is enabled, the data that's on the data bus, whatever value is on the data bus, is going to be updated and appear on the output. Now, we want to make sure that if we look at this example, our device that's holding the state of that output is a latch, so the data only gets latched in when the write signal or the enable signal goes back to the inactive state. So it's at this point here that the data is actually latched. So we want to make sure that when we're latching the data, that the data bus, the value on the data bus, is still valid. It's still the value that we want to write out. Okay. Now, if this were a edge triggered storage, maybe this device is implemented with a flip-flop instead of a latch. In that case, the rising edge of the write trigger might trigger the data to be latched at the output, but I always like to play it safe and make sure that my entire write signal going high and low all occurs within the period that the data is valid on the data bus. Even though if it's an edge triggered device, I technically only need it to be valid during this rising edge, and we know that our memory devices and our I/O ports have some setup time, write time, and hold time, but that we have to adhere to. But again, I like to make sure that the data stays valid until my write signal goes back to an inactive state. Then it doesn't matter if it's an edge triggered or level triggered device, the timing will work for either one. Let's look at a slightly more involved example of an I/O port. So here we have an I/O port that has separate data lines dedicated to the input channel and the output channel. So you'll note here that this input channel, so this is an external connection, that's an input. All right, so data is flowing into this channel. Let me use green. I think I was using green earlier. So this is my input connection, and we see that that connection goes to D0. Okay, let me try to follow this line here. Okay, so that is going to D0, whereas my output port, or my output connection, is coming from D1. Okay, so this is you know, it's not uncommon to have different bits of a port dedicated to doing different things. Maybe some are inputs, some are outputs. So we have to know the details of the port we're dealing with. You'll also note that this port, this I/O port, has gone and embedded the address decoder internally. We just show it kind of as a black box here, and show that it is configured to only respond and generate a chip select for a very specific address. Okay. The other thing you might note is that, and this is fairly common, although we haven't been really using this to date. The control bus signals on this I/O port are active low, so they're looking for a low state as is required by this inverter here to activate the write signal and the read signal. Okay, so as we you know, when we see a device like this, we're often going to be we're often going to be presented with some defining documentation that describes how to use this I/O port, and we've experienced a bit of this in the lab as we've been writing code to interface to the switches, although they're virtual switches and push buttons and LEDs. One of the pieces of information we need to know about those to be able to use those is their address. So here's a typical, you know, an example of what you might be presented with for documentation of an I/O port like this. Right away you see the address that the I/O port sits at. You see how many bits it has associated with it. The number of bits may not be the full size of the data bus. In fact, this one says it's 8 bits, but when we dig in a little bit further, we note that, well, actually 6 of those bits don't care. They're actually not connected. They are unused, and it's only the least significant bit that's associated with the input port, and the next bit 1, that's associated with the output port. Okay, and you see a little bit further description of each of the bits down below. Bit 7 through 2 unused. Bit 0 is a read-only bit, right? We can only read from that value, and the bit 1 is a write-only bit. Okay, so we can only write out to that port. Okay, and further to that, it says that in the case of the read-only port or bit of the port, writing to bit 0, right? Writing to anything to D0 is going to have no effect. There's no path for a write here. Okay, and the bit 1, this bit is undefined when reading, right? If we read from this bit, we're just reading the input to that D latch, which is not going to give us any valid value. Okay, so it's really unlikely that you're going to be provided details like what is in the diagram here at the top when you look at the documentation for an I/O port. Much more likely you're going to be presented with a description of the I/O port that looks like this, much more generic, just a block diagram for the I/O port, and a description of what each of the bits represents in that I/O port. In this way we're representing the I/O port as a register, right? Just an 8-bit value that can be read or written to. Of course, some of the bits are irrelevant when we're writing to them in this particular example, and some bits are irrelevant when we're reading from them. Okay. Further to this specific description goes on to describe the actual physical hardware that's connected to the output. So maybe this is a description that was provided for a development board, maybe like the board that we would typically use in our lab, and shows that the LED is connected on port B, and that putting a 1 on that output, writing a 1 on the output, right? You see here, causes the output to go on because it's driven through a inverter. Maybe this I/O port can't supply enough current directly. Maybe its I output, high or low, is not sufficient to power the LED. So we're using a inverter in the sinking configuration to drive this LED. And we also show the input port interface to a switch, and when the switch is open, as it's shown currently in the diagram, open switch is going to relate to a value of 1 on the least significant bit of this port. Okay, so far we've looked purely at the same type of kind of simple input and output ports that was actually presented a few lectures ago. But inputs and I/O ports can, with some additional hardware, be can be configured to be a bit more multifunctional. Okay, so the ports here, kind of from left to right here, we see an input port that's like the input ports that we've been looking at to date. We just use a tri-state buffer that allows us to enable that buffer to read a value from the input onto our data bus here. Okay, so that's our simple input port. It's read-only kind of device, and said quite simple. As is the write simple output port, which can only be written to, and again we put a value on the data bus as we showed in the timing diagram, and activate the write signal, assuming that maybe it's addressable. We aren't showing any address decoding here, but presumably it's at some address. Activate the write signal, and that data that's on the data bus will be delivered to the output port, whether it's a 1 or a 0. Okay, but sometimes it's often, in fact, it's handy to know what the last value was that, or what the current value is that's written to that output. Okay, you know, if for example we have an LED tied to this output port, it might be nice to know whether that output port is a 1 or a 0 without needing to track it in software and keeping some variable. By adding this additional tri-state buffer here, it allows us to read the state of the output port, so we can know, oh yes, it currently has a 1 on the output, or sorry, a 0, or it currently has a 1, and depending on what it's controlling, we will know the state of you know, whether the LED in this case is on or off. Okay, so that's a still a simple output port, but with the capability to read back the current state of the output. Okay, so this would be a read-write output port. So that might lead you to think, well, why can't I have a port that if I can read from an output port, why can't it be an input port at the same time? Well, in this particular case, I couldn't just tie a switch to this output port, because my switch, the state of the switch here and the state of this D latch might be conflicting with one another, right? Maybe this switch is being closed, right? Maybe I close my switch and put a 0 here, and maybe this D flip-flop has a 1 on it, so now I have a short circuit between this 1, this whatever that logic level is, maybe 5 volts, and this 0 that the switch is trying to present. So I can't tie any inputs, right? I can't make this an input without being able to isolate the output of the D latch, the output of the port from that that external pin through the addition of this tri-state buffer. Okay, so now I have the ability to, through the control of an extra control line here, if I write a 1 on this control line on this tri-state buffer, that's going to connect my tri-state buffer, the output of my D latch, to my output pin, and now this is acting like an output. Okay, and I can still read the state of that output back through this read signal if I want. I just can't tie anything to it and have it act as an input unless I put a 0 on this tri-state buffer control signal. That'll disconnect the tri-state buffer and really just leave this path into the data bus, which then would allow me to use this pin, this common pin, the same connection that was previously an output could now be used as an input. Okay, so that is what we would call a bidirectional I/O port that can be configured to be an output port, or it can be configured to be an input port. But now you might be asking yourself, okay, but now I have to have some means of, this bidirectional I/O port is a great multi-purpose, versatile port that will serve lots of needs, because it can be an input and an output. While it's an output, I can check to see its state, but I have to have a means of controlling this output and input state to control what is currently configured as. And looking back at if I think about my control bus, right, I don't have any means through my control bus of controlling that input and output state. So here's where we introduce the concept of a control register. Okay, so a control register is really a form of memory that its purpose is to control the action of a device within the system. Okay, we might even think of our control register as being an output port, right? And whatever value we write into this control register, right, we can through a write of the control. Sorry, let me back up. Through putting a value on the input of this control register. This control register happens to be connected to D2 of the data bus. So if I put a value on D2 of 1, and then I activate the write control register signal, that'll put a 1 at the output of this control register. That 1 will appear on this bidirectional I/O port, the tri-state buffer that controls whether it's an input or output. In this case, it's going to allow it to be an output. Okay, so by setting a 1 on this bit in the control register, we'll configure this port as an output. Now, maybe I want it to be an input instead. Well, I could put a value of 0 on this on line D2 of this control register, activate the write control. That'll latch a 0 into this control register. That 0 will be held here, causing this tri-state buffer to be inactive, and now I have this bidirectional I/O port configured as an input. Okay, so often these there will often be control registers for many different types of hardware devices in our system to be able to configure them, but in the case of a bidirectional I/O port, it may be a control register that's simply there to just set whether it's an input or an output. Other registers that you'll sometimes see with a I/O port will be the ability to turn on internal pull-up resistors, the ability to configure the the I/O port to trigger interrupts or something like that. So focusing just on an I/O port example like we've been looking at, this I/O port, and I've just shown one bit of this I/O port, but if we assume that the I/O port had 8 of these, 8 of this circuit that's shown above here, one for each bit on my data bus, then I would have to configure a control register for each bit of that I/O port, right? And that's what is shown here in this control register description. It's showing that I have the ability to set each of the bits associated with my my I/O port. I can configure each bit as an input or output by setting each of the bits in my control register. While this I/O port will likely also have a description of what is expected when you read from the port itself, which we may refer to as the data register. Okay, so we refer to, when we read or write to the actual I/O port section of this device, that is what we might refer to as the data register. It's likely going to have a unique address, and the control register will have a unique address as well, so we can access them separately in this system. But again, we need to make sure we know how we've configured the control register, so we know if each of the bits is an input or output, and then our data register will give us the ability to write to each of those bits or read from each of those bits of the I/O port. Keeping in mind that a read in some cases might be giving the state of the output when it's still configured as an output port, but if it's configured as an input port, the read is actually giving the state of the input and whatever is connected to that input. Okay, let's kind of combine this all together and look at an I/O port that has the control register built in, has our data register, which is really our I/O port, has the address decoding built in. So here we see that we can see here's the input output port, gets configured as an input or output through whether this tri-state gate is enabled or disabled. That tri-state gate will be enabled or disabled through this control register. You'll note the address of the data register and the control register, and if you trace back the logic here, you'll see that the only difference between the address is the least significant bit. So this least significant bit is fed in here such that when it's a 1, presents a 1 on each of these inputs, and for these two they're going to be disabled because they're looking for an active low, so we're not going to be able to generate a write or a read, but we are going to be able to generate a write to the control signal or the control register. Okay, so that's where that least significant bit of the control register is different. The rest of the address has to be as shown in my address decoder to generate my chip select, which will put a 1 here. Then if I put a low on the write signal, that'll put my final 1 here. that will generate my 1 on this output to enable a value from the data bus. In this case, it's coming from D7 to be written into the control register. If I write a value of 0, this tri-state buffer will be set to a high impedance, so my device, my port, becomes an input. If I write a 1 to this control register, this allows my output port to be connected to the output. So now this is an output that I can write a value into as well. Okay, and of course I can it's an output that I can actually read the value back from as well. I can write to or read from the port by, again, the case where I put now a 1 on the least significant bit and these bits on the remaining ones. That'll put a 1 here on my chip select line. It'll put a 0 here on the least significant bit. That'll put a 0 on these lines, but it'll put a 0 here. So this AND gate circuit will never become active. And now a low on my read signal will present a 1 here and present a 1 here to allow this to be read, whether it's reading actually from the external input, or maybe it's reading from the state that's of the output, if this happens to be a 1. Or in the case where I put a 0 on the right signal, that's going to generate a 1 here, which will put a 1 on this line, causes now this output to become active, and puts a 1 on my enable that allows data to be written into this D latch, and assuming that we have this configured as an output, the data is going to be appear at the external connection of the device, and it likely will control something. Like discussed previously, when we have any piece of hardware within our system, we should have documentation that describes how it is to be used. So here's the documentation that describes the data register, and here is the documentation that describes the control register. Okay, so we can look at these and see, well, in this specific example, the only connection is to D7 of the data bus. So we see that D7 is the only one that's being used. All the rest don't care. But this I/O port could, of course, be extended to have all of this duplicated for all 8 bits, and then all 8 bits could have significance. We notice that the address of the data register is defined here. Says it's 8-bit, although 7 of them are irrelevant. Shows that we can read and write to it, and it's programmable to be an input or output port. And again, here's description of the individual bits. And you'll see that it says bit 7 here, which is coming from the input A. Here we only have one input, but we might have multiple. We'll see that it can be an input or output, but we have to see the control register to see what it's configured as. Focusing on the control register, we see it has a unique address. It's just a memory location, a register. You can think of it as a output port that controls I like to think of it more as memory that's controlling the function of some piece of hardware. Okay, so this control register is actually configured to be write only. The one we presented up above earlier actually was read and write. So this one has some limitations. Once we write to it, we would have to keep track of whether we last set it to a 1, in which case it's an output, or a 0, in which case it's an input. Okay, and again, only 1 bit is significant in this case because bits 0 through 6 are not used in this specific example, but often our I/O ports are multi-bit, and hence our control registers are also multi-bit. While we're on the topic of registers, as we've named them, really we're calling our I/O port now a data register, because we can really just treat it like a memory register that can be written to and read from. And now we have a control register. Another register that you're going to encounter within your systems is a status register. Okay, a status register is just as it sounds. It's a register that will often is read only, and it allows you to monitor the state of conditions of something in the system, maybe a piece of hardware, maybe the CPU itself. Okay, so status register is generally read only. You can think of it as said. The course notes talk about it as being an input port. That's a fair assessment, because often it's associated with some peripheral external to the CPU. I like to think of it more as a memory within some device that is reporting on the status or state of that device or that component in the system. Okay, so it allows monitoring of conditions within a computer. We'll just keep it generic. Okay, and next class we'll get into looking at a different type of I/O port, serial port that will make use of a status register.